Okay, we'll go ahead and get started here. So just for your information, this is being recorded, so it can be put on YouTube. We won't say any of your names and there's no like video, it'll just be recording the screen and whatnot. So that's just information for you. But this is CBE 4 review. So we'll go ahead and get started. This lesson, this CBE covers rational inequalities, exponential functions, logs with their properties, and then solving exponential and logarithmic equations. And there's also a problem where you have its graph and you have to like do the transformations and whatnot for it. So solving rational inequalities. Rational inequalities cannot multiply inequalities by a variable because we don't know if the variable is positive or negative. You use addition and subtraction to get 0 on one side of the inequality. So you have like two fractions on one side, and a lot of times there'll be like one number on the other. And so you want to set it equal to 0 because it's a lot easier to find solutions if one side is equal to 0. And so here's problem 1. 3 will do that.
Sweet. Okay, thank you, Hunter. So like Hunter said, our first step is going to be getting this whole thing to be equal to 0. So there's not a ton of room to write, so I hope this doesn't get too messy for you guys. We've got 3 over x plus 1 plus 1 is less than or equal to 21 over x plus 9. What I'm going to do first is I'm going to subtract the 21 over x plus 9 on the other side, so this whole thing is equal to 0. So this is going to become 3 over x plus 1 minus 21 over x plus 9 is less than or equal to 0. Okay? And what we're going to start doing is we're just going to start solving as though this is equal to 0. The first thing I need to do is to get a common denominator. So the 1 term here, it is essentially just over 1. Like we don't really have to worry about it. Also, am I writing too small? Can you guys see that? Okay, sweet. So I'm going to multiply everything so that it has a common denominator. And if I multiply 3 by x plus 9 over x plus 9, then all I've done is multiply by 1. But now it has, we'll get the common denominator. We'll multiply 1 by x plus 1 times x plus 9 over that same thing. Then minus, and then 21 over x plus 1 over x plus 1, x plus 9. Okay. Sorry, that's slightly illegible, but are we okay? Okay, sweet. So I can combine these all. They're all like terms now. And so I've got 3 times x plus 9 plus x plus 1 times x plus 9 minus 21 times x plus 1 is equal to 0. And all of this is over our common denominator of x plus 1, x plus 9. Okay, so I need to simplify my numerator so I can solve for the zeros of the function. So I know when it's crossing the x-axis. Because when it crosses the x-axis, that's when it changes from being greater than 0 or less than 0. And that's what we want to know, right? So what I'm going to do over here, I'm just going to write a note. So 3 times x plus 9, that's this first term. That is equal to 3x plus, what is 3 times 9? 27. So 3x plus 27. This second term is x plus 1 times x plus 9. That is going to be equal to x squared plus 9x plus 1x plus 9. Okay, so you could also just write that as x squared plus 10x plus 9. Yeah, what's up?
When you got, like when you were first adding or multiplying x plus 9, on the second one, where it's just 1.
This guy?
Yeah.
Yeah.
How come it changed to x plus 1? Wasn't it just one?
Oh, yeah, so this one, what we're doing is we're just multiplying by one. And so x plus one over x plus one is the same thing as x plus is the one, and x plus 9 over x plus 9 is the same thing as 1.
Okay, that makes sense.
Okay. So, if we carry on, we'll look at this third term. If we've got negative 21 times x plus 1, that is equal to negative 21x minus 21, right? Okay, we are adding everything on the right sides of these equal signs together. And so what's going to happen is we're going to get x squared. So that is, is there a way to change pen color, Hunter? I mean, okay, we'll use red again. But we'll take this x squared term right here. Now we need to find all the terms with x's. All the terms with x's is this 3x plus 9x minus 21x. Oh, and then this plus x here. So 3x plus 9x is 12x. If we had another x, that's 13x. And then we have to subtract 21x from that. That will give us minus 8x. Does anyone agree with me? Okay, sweet. Then we have to add up all of our just like constants. We got 21 plus 9 minus 21. So 27 minus 21 is 6. Plus 9 is 15. Okay, my pen got fatter and I'm not sure why, but we're gonna work with it. Okay, and so that is all over my common denominator of x plus 1 over x plus 9 is equal to 0. Okay, now I need to factor my numerator so I can solve for my zeros, right? This guy factors, we need something that multiplies to 15 and adds to negative 8. So what jumps out to me is x minus 5 times x minus 3. And that all will be over x plus 1 over x plus 9. And that is equal to 0.
Is it gonna be equal to 0, or would we have the inequality to 0?
Yeah, so is it equal to 0 or do we have the inequality? Technically what we're solving for is the inequality, but our method for finding that inequality is setting it equal to 0 and finding out when it crosses that x-axis and where our asymptotes are. Once we know that, we're gonna decide whether it's positive or negative between each of those critical values. Okay, did that answer the question? What's still confusing?
You can just keep it as
Oh,
an
okay.
inequality if that makes more sense. to
That
you.
makes sense.
Yeah.
Okay.
You can do it either way. Thanks, Hunter. I will stop using your name.
We can use our names on it.
Oh, I will keep using your name. Okay, so our zeros are, so our next step here is to solve for when the numerator or denominator equals 0. So when our numerator is 0, then we have zeros of the function. So we have a 0 when x equals 5. And we have a 0 when x equals 3. And I got those just by looking here. So those are the zeros of the numerator, right? Okay, and then when our denominator is 0, we have an asymptote. So basically just a value that our function can never ever be equal to. And we'll have one of those when x equals -1, and we'll have one when x equals -9. Okay, so about this point is when we create a number line. Since this thing is equal to 0, or we could also think of it as this thing is less than or equal to 0, we want to know when it's negative, right? So negative values will be included in our interval, positive values will not. So at -1, we have an asymptote. So sometimes I like to think of it like that, like you just have a line going through there that your function will never be equal to. We also have one, label this guy -9. This is -1. And then we have a 0 at 3, and we have a 0 at 5. Okay, And we want to know whether the function is positive or negative between these points. The way we do that is by testing values in between these points. So we can test when x equals 10, we can test f of 10. So if we do that, I'm just going to plug it into the equation right above. So we'll do 10 minus 5 times 10. Whoops, sorry, I meant to do a negative 10. Sorry guys, my handwriting is absolutely atrocious on this iPad. So we got negative 10 minus 5 and negative 10 minus 3 over negative 10 plus 1 times negative 10 plus 9. Okay. Negative 10 minus 5 is negative 15. Negative 10 minus 3 is negative 13. Negative 10 plus 1, negative 9. Negative 10 plus 9 is negative 1. Okay. So at this point, what I realize is that in my numerator, I have a negative times a negative. Two negatives make a positive. And so negative 15 times negative 13 is going to become positive. So I'll just write a plus sign. In my denominator, I have a negative times a negative again. So that is also going to be positive. So I'm going to have positive values for my function below negative 9. Okay. And if we look back up kind of at the top, we're looking for values that are less than or equal to 0. So anything less than negative 9 is not going to be included in the interval. Okay. And then you go through and do that for each of your endpoints. I'm wondering if there's more room on another slide. Will anyone be really mad if I use this title slide? Okay, sweet. Okay, I'll just rewrite our number line. We've got an asymptote at negative 9, asymptote at negative 1, and then we've got 3, and we've got 5. Okay, we checked here, and this is positive. Okay, we can check the value for, let's do negative 5. That's in between negative 9 and negative 1, right? So f of negative 5. We will plug it into that original equation we were using last time. It's negative 5 minus 5 times negative 5 minus 3 over negative 5 plus 1 times negative 5 plus 9. Okay, negative 5 minus 5, negative 10, negative 8, negative 4. And then negative 5 plus 9 is a positive 4. So in our numerator, our two negatives will make a positive value, but we have a negative times a positive that will create a negative value. So a positive over a negative will create a number that is overall negative, right? And so between this interval, we're going to have negative values. Okay. Let's do this next one. We're going to do 0. 0 is between negative 1 and 3. So you've got 0 minus 5, 0 minus 3, 0 plus 1, 0 plus 9. So negative 5 times negative 3 is going to be a positive. In this case, it's positive 15. That's really easy for me to do in my head, so I'll do it. And then we have a positive 1 times a positive 9. This is indeed a positive number, right? So between here and here will be positive, and we will not include it in our interval. Okay, we're going to do the number 2. That is between 3 and 5. So sorry, this gets a little tedious. 2 is not between 3 and 5. Oh man. We're gonna do 4. That was embarrassing, guys. How come none of you stopped me? Okay, 4 minus 5, and then 4 minus 3, and then 4 plus 1, and 4 plus 9. Okay, 4 minus 5 is negative 1. That's negative 1. That's positive 5.
That's negative 1 and a positive 1.
Yes. Say that again. 4
It
minus
should
5
be
is
positive.
1. 4 minus 3 is positive. Okay. Do we agree now? Okay, you guys have to speak up. Okay, so negative times a positive is going to be negative, in this case, -1. 5 times 13 is gonna be a positive. If we have a negative over a positive, what's gonna happen? Yep, okay, sweet. Let's do the last one. We just have to pick a value bigger than 5. Okay, we'll choose 10. You've got 10 minus 5 times 10 minus 3. Again, I apologize that my handwriting is atrocious on this. But Hunter says his will be worse. Okay, 10 minus 5 is 5. And then we have 7, 11, and 19. This is positive. That's positive. A positive over a positive will result in a positive number. Okay. From the previous slide, we remember that, like this handy dandy little arrow says, we're looking for numbers that are less than or equal to 0. So on our number line, this number line is kind of like the x-axis, right? Our up and downs represent asymptotes. These are values that the function cannot be. The circles are values that the function will be, right? There's a function crossing through those zeros, right? So we want to know when it's less than 0. So we don't include negative infinity, it's positive down there. We don't include -9 because that's an asymptote. But we're gonna go from -9 to -1, and we won't include -1 because that's an asymptote. And we'll take the union of that, but it'll be a hard bracket because 3 is 0 to 5. And after that, it gets positive again. And so that will be our entire solution. Yes.
So in this format of problem 1, will it always be greater than or less than? So it'll always be bracketed on one of the ordered pairs?
Could you state that question one more time?
Yeah, so like if it was like less than, then it wouldn't be a bracket, it'd just be a regular parenthesis, right? Or we always see brackets in this question.
From all the ones that I've noticed, it's all greater than or equal to or less than or equal to.
Okay.
But you're right, if there isn't an equal to, it would all just be brackets.
Okay.
Or just parentheses, I mean, not brackets.
How do you know, sorry, you go. I was gonna say, how do you know which of the two is going to, is it gonna be based on, because those are greater than 0?
So like, how do you know whether you're looking for positive or negative values?
I guess I'm asking which one is gonna have the brackets versus the parentheses.
Yeah, so we decided that these were asymptotes, right? Because over here in our denominator, I'll point an arrow to it here. There's our denominator, right? But in our denominator, x cannot be -1 and x cannot be -9. So these are values of x that can never happen. So those will be soft brackets. Okay, in the numerator, we said, okay, x is equal to 5 and x is equal to 3 when we're crossing the x-axis, right? So those will be included because they're less than or equal to 0. Okay, what questions do you still have about that?
I think that makes sense.
Okay, what's up?
So since it was less than, we're finding negatives. If it was greater than, would we be finding a positive?
Yeah, so if we wanted the greater than, we just look for the positive values. Okay. Sweet.
All right. We will now move on to the next problem. So with exponential functions, these are just the basic rules. And so if you're multiplying two things together with the same base, then you can add the exponents together. If you're multiplying, if these two are multiplied together and they're both raised to n, you can distribute that through. And if it's to a negative power, that means that it's going to be in the denominator. And these will be helpful when we're moving on to the graph here. And then if it's in the, let's see, if you have one in the numerator and one in the denominator, it's subtracted. And then the others are just kind of going through it. One key one though is this one at the end here. So for instance, if we had a square root of x, Another way you can write this would be x to the 1/2. If you take any math classes past 1050, especially in calculus, being able to go between these two, like square roots and putting it in the exponent, will be very helpful. And then this shows any number raised to the power of 0, as long as the base is not 0, is equal to 1. Okay. So now we'll go to graphs. So the parent graph, any number to the x, it'll look something like this, where you have this point at 0, 1, and then it'll go and raise up, and it does not ever cross the x-axis. Because if you raise any number to a power, it's never going to be a negative number. Okay, and so when we move on to this graph here, then if we keep that in mind, where we have the parent graph, looks like this, we can kind of look at the transformations that go on here. For instance, in the parent graph, it's never going to cross the x-axis, so that would be the equation y equals 0. In this graph, you see that it never crosses this point here. It never crosses y equals 1. And so that can help us out with these transformations. And then you also have this point here at 2, 0, which will help out, and 3, -3. So if we start with the asymptote, the part at y equals 1, you see that never crosses there. So imagine that you have this, the original equation would be like y equals plus or minus a to the x plus or minus b plus or minus c. And on the CBE 4, it'll give you that equation right there to help you out. So we know that c is going to be a positive 1 because it got shifted up 1, that horizontal asymptote that never crosses is 1 above what it usually is in here. So you know y equals ax to the minus b plus 1. Now we want to look at this point here at 2, 0. And I guess before that, you can also look, and this graph kind of got reflected over this horizontal asymptote. Imagine if you had this, and instead it just went like this, but there wasn't a reflection, or there wasn't a translation up. This is the same as a -8 to the x, because you have the reflection over that asymptote. And so in our equation here, we know there's going to be a negative there because of that reflection. Now we can look at that point 2, 0 and say at that point, you have the fact that y is going to be 0. Yeah, so y is 0. So if we plug that point into this equation, you have 0 equals -a to the 2 plus b plus 1. I just plugged that point into the equation we have there. And now you subtract 1 over. And if you divide by, or I guess let's add the a 2 plus b over. So if you have an a to the 2 plus b equals 1. If we use the rule that anything raised to the power of 0 equals 1, then we can solve for b in this case. Because if you have a raised to the power of 0, essentially you're saying a to the 0 equals 1. Therefore, a to the 2 plus b has to equal a to the 0. And so from that, you can know that b is going to be -2. Because what's going to make this equal to 0 is when b is -2. And that, so you have now y equals -a to the x minus 2 plus 1. So the last step is to solve for a. To do that, you want to plug your other point into this equation, and then you can solve for a. I'm going to move up to this space here. So if you have a -3 is the y value, with -a, x value is 3 plus 1. If we solve for a, you subtract the 1 over, so you get -4 equals -a to the first power. Divide by -1, 4 equals a to the first power. And a to the first power is just a. So a equals 4. So if we plug that all back into our equation, you get y equals -4 to the x minus 2 plus 1. And this would be your final answer. Yes.
So is C always gonna be just where, like, no matter what the graph, if it's reflected or not, is C just always gonna be where it flatlines closest to the x-axis?
Yes. Any other questions? Okay. We'll move on to the next part, which is logs.
So logs are super fun. This is super important. This is what I remember so that I remember how to do my logs. But the expression log base b of a represents the number you would have to raise b by to obtain a. It's the number you have to raise b by to obtain a, okay? So log base e to the x is called a natural log, and it's just written as ln of x, natural log x. And log base 10 of x is the common log and is written as log base x. Logs are the inverse of exponentials. Yeah. Okay, so these are super important properties of logs that we're going to be using. What we notice here on this very first one is we have log base a of m and log base a of n. They have to have the same base for this to work. But what we're doing is we're adding these two logs together. And when we do that, we can combine them through addition just to become this one problem where it's just a multiplication problem. We can go both ways. So we have multiplication, we can split it up into addition, or we can take addition and smash them together and make them become multiplication, right? The kind of the same thing will happen here. If we have log base m minus log base n, this will become a singular log, but with division instead, okay? And this property is super fun. If we have an exponent, not an exponent, a constant hanging out in front of our log, what we can do is we can basically just bring him around and make him an exponent in the log, okay? So these are three super important properties that we're going to be using for the next few problems. Okay, this one we need to know. So if we don't know how to solve a log per se, then if we have all positive real numbers, then log base b to the x is the same thing as log base c to the x or log base c to the b. What basically happened is this b here became this b in the denominator, and this x here became this x in the numerator. I realize I just made that totally illegible, but that's the idea. Often what we'll do is we'll make that c equal to 10, so we can type these into our calculator so we can evaluate logs of this form, okay? So this is also an important property worth noting and memorizing, okay? Second thing, if a is a positive real number, then log base a to the a of x is equal to x. Because what this is saying is, what power do I have to raise a to, this little guy? So a to what power is equal to a to the x? So a to what power is equal to this? well, that's just gonna be x, right? So if you do that, then your value for that is just gonna be whatever the exponent is. The same thing, the reciprocal is kind of true. If you raise a to a logarithm, then you will result in just the, I don't know if I know what that's called, the argument of the logarithm. Don't quote me on that, okay? But you will just, the thing inside the logarithm, that's just going to be what your solution is, okay? So these are super important properties that I would try to make part of your brain. So we're gonna be using these properties to solve problem number 3. First thing, we have an exponent outside of this log here, so that, not an exponent, a constant, which means that we can make it an exponent inside this log. Since this log is taken to the root 3, if we raise something that has a cube root, if we raise it to the power of 3, they basically just demolish each other and we're just left with what's inside. So what we'll have is log base b of b to the 6th over k to the 4th minus log base b of k to the 4th b to the 8th plus log base b k to the 8th b to the 5th. Okay. My personal preference is to combine logarithms with addition first. I make less mistakes that way. So now that we've got our logarithm to this point, we want to simplify and condense it further. So we want to make all of these to become one term. So I am going to combine these two terms together. Since they are logs with the same base that are being added together, we can multiply what's inside the log together. So I'm just gonna carry down this term. I'm not gonna do anything with him yet. It's gonna become b to the 6th over k to the 4th minus log base b of k to the 4th times k to the 8th. Did I write that down wrong?
It's just you're gonna be doing it wrong.
Yeah.
You're taking out a negative without,
Yeah.
because what you'd have to do.
I did this right 4 seconds ago.
Yeah. So let's go, where's the eraser? Oh, so let's take whatever has the positive, that means it's gonna go in the numerator. Whatever has the negative is gonna go in the denominator. So if we go back into here, so we have the negative log base b of k to the 4th, b to the 8th, plus log b, k to the 8th, b to the 5th. That's just exactly what we have above. So now log b, this first term is a positive, so all that's going to go in the numerator. Second one's negative, that's going to go in the denominator. The third one is a positive, so that goes in the numerator. So now from there, we can simplify what's inside there. So that's going to equal log b. You can see there's a b to the 6th, a b to the 5th. So that's going to cancel. That'll become 1. So you have a b to the 1st. You have a k to the 4th and a k to the 8th. This is a multiplied, by the way, not a subtract. And so when you multiply those together, you'll be left with a k to the 4th, because this will cancel. That will become a 4. And then in the denominator, we haven't done anything to it yet. And now we can simplify once more. You have a k to the 4th here, cancel with the k to the 4th there. So you're left with a log b, and then there's a 1 here. That'll be a 7 in the denominator. Log b of a 1 over b to the 7th. From here, we know that this is in the denominator. So another way you could write this is negative log b to the 7th. That's a 7. This is base b. And so log base b of b to some number is just going to be that number. So you're left with a negative 7 as your answer. Is that the answer? Negative 3. 4, 0, 6,
I got a positive 3, but I got it.
11. Oh, something I did wrong in the, so I did something wrong in the simplification here. B to the 6th, B to the 5th, that's B to the 1st, B to the 8th in the
Would that
denominator.
be b to the 11th?
Yeah, aren't you adding them?
Because that second b is still in the numerator.
The second what?
The second b to the 6th.
Oh,
B to
yeah.
the 5th.
So that would be B to the 11th there. B to the 11th over B to the 8th. So that's what I did wrong. I subtracted them, even though both of these are still in the numerator. So you'd have to add them together. I acted like one was in the denominator and I subtracted it. So silly me. Don't do that on the test. So if we rewrite that over here, this would be log b, b to the 11th, k to the 4th, over k to the 4th, b to the 8th. When you simplify that down, you would end up getting a 3. Yes.
So since the first, the k to the 4 is in the denominator, but also the numerator, you still subtract it?
Yeah, so this is, if you had like, let's say you had a 1/2 over a 2. Another way you could write this would be 1/4, because this is the same as 1/2 times by 1/2. So yeah, because the k to the 4 is in the numerator, it's still like subtracted because it's in the denominator.
So how come it's not a negative?
A negative 4? What do you mean by that?
Just because then it would be negative 4 minus 8.
Should be a
Or 4
negative 4 plus 8. Because the 8 is in the numerator, the k to the 4th, it would be like a negative 4,
Oh,
but then you would add them together.
oh, that makes sense.
Sorry if I confused you by messing up with the b's there. Are there any questions? Okay. And we'll move on. Are you doing number 4?
Yeah.
Okay.
Alright. Okay, so this one, first thing you want to do is look at what you're given. We know log base b of 5, and we know log base b of 30. And what we're given, we want to find this. So we have log base b of 1/6. So I can rewrite 1/6 in terms of the logs I'm given. So 1/6 is the same thing as 5/30. And I know the value of log base b of 5, and I know the value of log base b of 30. So I want to get it in this form. Okay, once that I have this as a division problem, I can split it up using subtraction with 2 logs, right? And so my numerator will be my first log, log base b of 5, minus log base b of the log that has the denominator. And then, once we know these values, we'll just substitute what it's given us. We know log base b of 5 is 1.922, and log base b of 30 is 4.062. And I don't have my calculator on me or anything. Okay, but does anyone have any questions on how I did that? What's up? Okay. So if I take 1.922 minus 4.062, I get negative 2.14. And That is the answer. Okay? So for this one, look at what you're given and look at what you have and see how you can rewrite what you have in terms of what you're given. Okay? So, question 5. You got this.
All right. So solving exponential equations, what you want to do is you want to get all your exponential stuff on one side and everything else on the other side. And so I think the easiest way to see that is if we get to an example, and you would do the same thing with logs as well, as whatever you have the log, put on one side, everything else on the other side. So we'll go with problem number 5. It says solve the following equation, round your answer to 4 decimal points. So you're given a 2 ln of x plus ln of 10 equals 3. So what we can do, there's a couple options here. You could combine the natural logs together, but what I like to do is I honestly just keep them separate. And I take all of this and raise it to the e. And what you do to one side, have to do to the other side. Because the opposite of the natural log is if you do e raised to the natural log. And so what this would be is e to the 2 ln x plus e to the ln 10, or actually that's times, sorry. Because if they're added in the exponents, for instance, if this were like an e to the 1 plus 2, that would be the same as e to the 1 times by e to the 2. So that's what we're doing here, is we have e to the 2 ln x plus ln 10. So you have e to the 2 ln x times e to the ln 10. And that's going to equal e to the 3rd. Now this e to the 2 ln x, because the ln isn't quite by itself, what I want to do is I want to put this 2 inside the natural log so that I only have the natural log there. So to do that, I have 2 ln x. We can use our property that says that if there's a constant out in front, we can raise the number inside the log to that constant. So 2 ln x equals ln of x squared. Or another way you could think about this is 2, if this is in the exponents here, you have e to the 2 ln x. If a number in the exponent is raised to the same thing, then you could say this is e to the ln x, all raised to the 2nd power. Either way, you could think of it that way, and it'll give you the same answer. Because in this case, the e and ln will cancel and you'll just be left with an x squared. In this case, this is all raised to the e. And so then the ln and the e would cancel and you'd be left with an x squared. So if I go back here, you have e to the ln x squared times by e ln 10 e cubed. So this, once we simplify, you get x squared times by 10 is 3. Yep. 10x squared equals, sorry, not 3, but e to the 3rd. And then you can solve for x squared. So x squared equals e to the 3rd over 10. And x would equal, in this case, can x actually be positive or negative? If we were to plug in, and can we plug in a negative x into that ln? The answer to that is no. You cannot take a log of a negative number. That's just one of the domain restrictions, is whatever the value that you put into your log has to be a positive number. So x would not be plus or minus the square root, but only the positive thing is square root e to the 10. E cubed over 10. And then you can plug that into your calculator.
We should get 1.4172.
1.4172. Questions on how I did that? Okay, then we'll move on to problem 6.
Sweet. Okay, this one looks really scary, and it's only kind of scary, not really scary, okay? So what we're gonna do is we're going to make it so that both expressions that contain an e are on the same side. So we're gonna multiply this side by e to the 3x plus 8. And then we're gonna do that to both sides. E to the 3x plus 8. And we're gonna multiply both sides by 20 so that we don't have anything in our denominators, and so that e is on just the same side. So this 20 and this 20 will divide out. And then this term and this term will divide out. So what we'll be left with is the following. Okay. Are there any questions up to this point? The 5, what I did is I said 5 times 20 is 100.
Oh,
Yeah, so that's where that 5 went to. I magicked it away, I guess. Okay, so let's make a note here. If we have 2 squared plus 2 to the 3rd, then we just have 2 times, times, thank you, 2, we have 2 times 2 times 2 times 2 times 2, right? And so that's just gonna become 2 to the 5th. All we did is we added their exponents, right? So that's what we're gonna do for these e's. Their exponents are just a little scarier than 2 and 3, right? So what we're gonna do is we're gonna take e to the 3x plus 8 times 7x minus 12. And all added together is equal to 100. Sorry, guys. I just ate my words. Okay, all clear? So, I have this, and I'm going to choose to simplify it. 3x plus 7x is 10x, and 8 plus negative 12 is negative 4. All of that is equal to 100. The tool that we have for undoing e to a power is the natural log. We'll remember, we'll make another note. The natural log of e to the x is just x, right? So if we take the natural log of this side with the e, our result is just gonna be whatever is in the exponent. So I'm gonna take the natural log, I'm gonna result in that, but I have to do it to both sides, so I'll be left with the natural log of 100 on the other side. Are there any questions on how I did that verbal step? Okay, I'm seeing mostly confident faces, so I'm gonna move on. Now all I need to do is solve for x. So I'll add 4 to both sides, 10x equals natural log of 100 plus 4. And so if we divide that whole thing by 10, we will have solved for x. Did you get a number? Okay. Sweet. We didn't get a solution, but I can confirm that is right. I checked with another thing. Okay. Sweet. Okay. Yeah.
So, with this, you said you didn't get an actual answer. Is it going to ask for some sort of value, like a physical value, like negative point, whatever that number is, or is it just, do I just plug this?
I kind of think it's gonna ask for a 4 decimal approximation on this one.
I think on this one, you can put either or.
Okay.
If
Yeah.
it some of them will say you can put it in exact form or 4 decimal approximation, and some of them only accept the 4 decimal
I
approximation.
guess just read the question.
Yeah.
Read the question. Yeah, make sure you read it and know how it wants you to answer, because it would be really sad if you did the problem right and got it wrong. Because you typed it in how it didn't want.
When you put it in the calculator, do you have to put the 10 in parentheses for it to divide by all of it?
So you'd have to do the ln of 100
So this is what you type
and
in your
then plus
calculator.
4 all in parentheses divided by 10.
Yeah, you do it like that. That's what you would type in your calculator. My personal preference is to just go term by term and just do natural log of 100 and then write down that decimal and then add 4 to it. Write down that decimal and then divide by 10. I find I make less mistakes that way. Not everyone's that way, so do whatever is best for you, but that's my method. Okay?
I don't know if you guys talked about it before I got here, but what calculator, if any, are we going to be given?
It's an on-screen calculator.
Do you know like how powerful it is? Is it just like the equivalent of science?
It has log base 10, natural logs, and like e to the power, just basic stuff like that.
Yeah, it'll be the same thing as that's on your practice things. Okay, so we're gonna move on. Problem number 7, solve the following equation. In order to solve this guy, we have to, it says it on the PowerPoint. We have to rewrite 9 and 27 as exponentials with the same base. Some of us see this as soon as we look at it, and some of us are like, right? So the way we can do to solve that is to just make a factor tree. So 9 can be split into 3 and 3, right? And then 27, I know 27 is equal to 9 times 3. And that can be divided by 3 and 3. So now I know that I have 2 3s that are for 9. So 9 is the same thing as 3 squared. And 27 can be broken down into 3 3s. So 27 is the same thing as 3 to the 3rd. Okay. So I can rewrite these as though they have the same base. So 9 to the negative 3x equals 27 times 2x plus 2. I'm going to rewrite 9 as 3 squared is equal to, oops, I forgot his exponent, negative 3x times 3 to the 3rd raised to this power. Okay? When we raise a power to a power, we're going to multiply them together. So what's going to happen is we're going to get 3, and then we're going to multiply 2 by negative 3x. And I'm so sorry, this is barely legible. I'll try and write bigger. More legibly, I guess. So that's going to happen here. This side will have a base 3, but now we're going to multiply 3 by 2x plus 2. So we're going to get 6x plus 6. Okay. Now that these have the same base, I can just solve this equation like this. It's just going to become negative 6x equals 6x plus 6. Okay? Because 3 to a power, if 3 to a power is equal to 3 to a power, then they better be raised to the same power, right? So we can kind of just ignore a 3 and solve for the powers. When I do this, I am going to subtract 6x, I guess. And so I'll be left with negative 12x equals 6. So I'll divide both sides by negative 12, and I'll get that x is equal to negative 1/2. Okay. Any comments or concerns about that?
All right. Moving on. All right, so we are going to talk about exponential growth and decay. These are some basic equations. You have function of time is equal to the initial amount, e, times the rate times time. And when I work through a problem, this will make sense what this is talking about. And then the differences of magnitude is the magnitude of 1 minus the magnitude of 2 equals the log base 10 of the difference of their intensities. So, and the test will at least give you this one. You will want to know this one though. So, using models. Okay,
Can you remember it just as the PERT formula? PERT. P is your initial population times E raised to your rate times time.
so problem 8 here. You have a biologist puts a population of 300 bacteria into a growth medium at 8 a.m. So what I like to do is as I'm reading the problem, I kind of identify what they're giving me. So at first they're saying that they're giving 300 bacteria at the start. So that's going to be your original amount is 300. Okay, and then she measures the sample again at 4 p.m. Between 8 a.m. and 4 p.m., that's 8 hours. So when t equals 8 hours, the population is 750. When t equals 8 hours, so this is p initial is 300, p equals 750. So p initial is, this is the initial amount, the second p, or you could say this is like y, either way, equals 750. Now it's saying what you want to find is how many bacteria will be there at 8 a.m. the next morning. So what we want to find is you want to find y when t equals 24 hours. So with this given equation, you have the equation with this given knowledge and the equation y equals p e to the RT. We know what p is. So you have y equals 300 e to the RT. We have 3 unknowns and we want to have it be an equation, you just want 2 unknowns. So you want y and t. And so we want to figure out what r is. We want to figure out what our rate is, our rate of growth. So we can use this knowledge that at 8 hours, there is 750 bacteria. If we plug that into our equation, you have that 750 equals 300 e to some rate times by the 8 hours. From there, we can solve for r. So you divide by 300, 750 over 300 equals e to the r times 8. So 8r equals ln, 750 over 300. So then r equals ln of 750 over 300. Sorry for my terrible handwriting. Over 8. Are there any questions on how I got r? Because if you know 2 of the variables and you plug that in, you can solve for the third one. So at this time, we knew that when t equals 8, y equals 750. And so because of that, we could solve for r. So now if we go back to our original equation and plug that in, I'm just going to say, what was r?
0.1145.
0.1145. So if we plug that into our equation, y equals 300 e to the 0.1145 t. Now, we want to find y when t equals 24 hours. So we can plug in 24 in for t and get an answer for y. So you'd say that y equals 300 e to the 0.1145 times by 24. And that would equal
4,688.
the one thing, yes.
If you were to plug in like 750 over 300 equals ER to the 8th, would that give you though, right? Like, would that be an equation that you can put in or no?
Like, are you saying it in this one?
So like before you switched the equation to where you have ln and then
Okay.
8r equals ln, could you put the equation before into a calculator and essentially get r still?
So you would have to solve for what R is. Because if you just plug like this into a calculator, your R is unknown and it's up here. And so there wouldn't be some way to plug that into your calculator. So you want to solve for that variable so you can plug, what you plug in your calculator is just numbers.
Yeah.
Yep. And then one note on time, you want to make sure that whatever you choose for your time, like this, we chose hours. We want to stay consistent throughout the whole thing. So even though it was like 1 day later, we couldn't put in a time of 1 because 1 day is not in hours. And so that's why we had to put in 24 hours. Some of the problems on the test will be like, it'll give you a half-life of, let's say, 8 days, and it'll say in 5 weeks, what is like how much is left. And so you can't just plug in 5 for the time, you have to do 5 times 7 is 35 days, and have to plug in 35 for the time. Are there any questions on problem 8 here? No, any other questions? Okay. Then you see it's 464,688. Now if we move on to problem 9, earthquake in California. So I'll write the equation up here. They'd give you this on the test. And the equation is the magnitude of the first earthquake minus the magnitude of the second earthquake equals log base 10 of the intensity of the first over the intensity of the second. So it says an earthquake in California had a magnitude of 3.15 on the Richter scale, and an earthquake in Alaska had a magnitude of 7.1. How many more times intense was the earthquake in Alaska? So let's make Alaska earthquake 1, because it's the bigger one. So if we say Alaska was M1 equals 7.1, and if we make California M2, that would be 3.15. And that's asking how many times more intense was the earthquake in Alaska versus the earthquake in California. So it wants to know, so you need to find what I1 over I2 is, because the intensity of Alaska divided by the intensity of the Californian earthquake will give you how much greater the Alaskan one was than the Californian one. So that's what you're trying to find. And now you have this equation up at the top. And so you can plug it into there. So I'm just gonna say I1 over I2 is X, because X is what we want to find. So if we say 7.1 minus 3.5 equals log base 10 of X.
3.15.
Yes, 3.15, thank you. Then to solve for X, you could get a value here, 7.1 minus 3.15 is at 3.95, I believe. Log base 10 of X. To undo log base 10, we would want to raise it to the power of 10, because 10 is the base. So you say 10 to the power of 3.95 equals 10 to the power of log base 10 of X. And you'd be left with 10 to the power of 3.95 equals X. And you'd plug that in your calculator. Let's make sure 7.1 minus 3.95, 10 to that power gives you 89. 12.5. Which when you round is 89.13. The one thing you want to keep in mind is it's this I1 over I2. You want to see which one, the one that is great, more intense, is probably the one that you want on top. Because then it will avoid having like a decimal value in there. And in this case, it's saying, how many times more intense was the earthquake in Alaska? So you want to know Alaska compared to California. So you'd want Alaska's intensity on top. So you want M1 to be Alaska, I1 to be Alaska, and then M2 to be California. The one that you're analyzing is the one that you want to be number 1. Any other questions on this one?
I mean, how common do they put the like weaker one as M1 as a value? I don't know, like you wanted this example, but
Yeah.
is there an option where we have to use a decimal or some sort?
Um,
I'm sure.
What
it's
they
the same
would-
process.
what they would probably say is how many times weaker was the one in California than in Alaska?
It's the
And
same.
so it wouldn't be like a decimal, it would end up being the same thing.
Okay, cool.
Or it would, well, I think it'd be the same.
It might be 1 over that.
Maybe, but you'd put whatever they're asking for, you want that to be number 1.
The same.
Yeah,
Yeah.
because it's that times weaker.
Yeah.
Okay.
But your algebra gets a lot harder if you don't set it up like Hunter explained. So like picture which one has to go on top and which one has to go on bottom.
Right.
But they're never gonna ask like what the scale is, because it would be like 1/8,913th of Alaska. If it asked like what's the value of California, that's like not gonna be something that's gonna ask.
Because I mean, pretty much what this is saying for x is I1 over I2 equals 8912.5. If you were to make it so it's not a fraction, you're saying I1 equals I9 equals that. So you're saying the intensity of Alaska, because that's what we said 1 is equal to 8,913 times that of California.
Perfect. That makes
Yeah.
sense.
Okay. Last problem is half-life. It says 100-gram sample of radioactive isotope decays to 22 grams in 200 seconds. What is the half-life of the isotope? All right. We can use, so half-life, what is half-life? Like, let's say we have a 100-gram sample and it goes through the period that is half-life. How much of that sample is left?
50 grams.
50 grams, exactly, you have half of it. So in that case, you can say if you have half, let's see if I'm doing this right. You still use PE to the RT on this one?
I think so.
Yeah.
Yes. You have to solve for the negative r.
Negative R. You have a 100-gram sample of radioactive decay. Okay. So you're saying, you want to do this one?
1 second.
You have Y equals PE to the RT. Or you can say, because this is half-life, this can be a special case, or you could say that Y equals half to some time over the half-life time. And this is, we'll say T sub H. Because this is saying that if T and T sub H, let's say your half-life is 8 seconds, okay? If you say that in 8 seconds, and your half-life is 8 seconds, you're saying that Y equals 1/2, and then there's also still a P out here, however much you have, to the 8/8, and you're saying that Y equals p to the 1/2. So in 8 seconds, half of what you originally had is going to be left. So with this knowledge here, we know that you could say your principal, your starting amount is 100 to the t over t, your half-life. So, and then it gives you that at t equals 200, at t equals 200 seconds, y equals 22. So if you plug that into the equation, you have that 22 was 100, 1/2 to the, and then this is 200 seconds on the top, and you want to find your half-life. So now we can solve for your half-life time here. And you can divide by 100, so you have 22 over 100 equals 1/2 the 200 over th.
Natural log of both sides.
Yeah. Okay, now you can take the natural log of both sides because your calculator isn't going to be able to do like a log base 1/2. It also can't even do a log base 2. So you'd have to do like a natural log of both sides. So if you say ln 22 over 100 equals ln of 1/2 to the 200 over h. Now we have the rule that if something inside the natural log is raised to a power, you can multiply that out in front of the log. So you have ln of 22 over 100 equals 200 over th times by ln of 1/2. And now if we're solving for t sub h, then you want to multiply that to the other side and divide by ln of 22 over 100. So I'll do that in 2 steps here so you can see it. And then you divide, so th equals 200 over. And if you were to plug that into your calculator, you get 91.56. Let's see, 200 natural log of 1/2 divided by natural log of.
That's what I call.
Good. Mine, I plugged it in wrong somehow. So,
Oh, I got it.
okay. Questions on how I did that? The key with this is the fact that you know that 1/2 of it is it's the whole half-life concept where at some time, half of it's going to be gone. And so you're trying to figure out what your half-life time is. Trying to figure out this. Okay, if there are no other questions, then there are other resources for you to help out with this CBE. You can go to the AMLAC. There's always tutors there. You can look on if you type in like USU AMLAC, then you can see when the recitation leader's office hours are as well. You go there, or there's the YouTube videos that they put on. And this video will be put on within the next few days.